In the last set of videos, I talked about the basics of multiple linear regression modeling, and I'm going to go on now to talk about, in a little more depth, various aspects of applied regression modeling in the context of multiple linear regression. And in this video and the next video, I'm going to talk about transformations. And in this video I'll focus on transformations of the predictor variables, and in the next video I'll talk about transformations of the response variable. So in the context of regression, a transformation is a mathematical function that we apply to a variable in our data set, whether it be one of the predictor variables or the response variable. And so to make this a little more concrete, I'm going to use an example where we are thinking that there may be a stronger linear relationship between y and the natural logarithm of x than there is between y and x itself. And so to determine whether that's the case or not, we're going to fit two models, one in which we're using the untransformed x, so that's model 1 here. Expected value of y is b0 plus b1x, and then model 2 is going to use the transformed x, so the natural logarithm of x, so expected value of y is b0 plus b1 times the natural logarithm of x. And we're going to ask the question which model fits better, and we're going to address that using the measures of model fit that we talked about earlier. So we're going to look at the regression standard error, S, and this gives us a measure of how accurate predictions from the model are likely to be. So we want that to be small so that the predictions are more accurate. We're going to look at the coefficient of determination r squared, so how much of the variation in the response variable can be accounted for by the model. So we want that to be as large as possible. And then we're going to think about a hypothesis test for B1 in each of these models. So how strong is the evidence that B1 is not 0? And so the larger the individual t-statistic for that parameter, then the more evidence we have that B1 is not 0 in the model. And so a larger t-statistic will indicate a better model. So we're going to look at this example here where we've got a bunch of different companies using TV advertising to promote their products, and this data set measures the number of retained impressions in millions from people watching these commercials on television, and we're going to try and predict that variable, the number of retained impressions, using the amount of money that's been spent on the commercial in millions of dollars. So you would expect to get more impressions the more you spend, but what is the nature of that relationship? So I've got the data here in R, so I'll take a look at it first. So here's the data. Not a very strong relationship, but there is a positive relationship of some kind, because the firms that spent more money did tend to get more impressions on average, whereas the firms that spent less money down here got less impressions. But it doesn't look like there's a linear relationship here. It looks maybe like it's a little more curved. If I trace out what I think the trend is in the data here, I think I would trace out a curved line like this. So let's fit our two models. So here's model 1, and we can look at those numbers that we were going to use to compare the models. So here's the regression standard error, R calls this the residual standard error, 23.5. Here's coefficient of determination r squared, 0.424, and then here's the t-statistic for B1 in the model, 3.739. Okay, so can we do better by using a transformation? So if we Actually, before I do that, let me just add the regression line for that first model to this graph so we can see what it's doing. Okay, and I don't think that's doing a very good job of tracking the trend in the data. Okay, so now we'll apply our transformation and we'll fit our new model with the transformed x, and we'll summarize that model. And now we'll look at regression standard error 21.18. Okay, that's a better number than we got before because it's smaller than 23.5, so that's good. Let's look at r squared. We get, I can highlight it, 0.5323. We want that to be higher than it was before, and it is. It was only 0.424 before. And let's look at the t-statistic. It's 4.65, and we want that to be higher than it was before, and yes, it is higher than it was before. So from those three measures, I would say we've got a better model by using the transformed value of that variable. Let's look at a graph of what that looks like. So now I've got log spend on the horizontal axis, and if I put the regression line from model 2 on here, I think that tracks the trend in this data quite nicely. So we've discovered evidence that model 2 is better than model 1 here, but the downside is model interpretation is a lot less straightforward. So we can get some idea of what the model is doing by looking at fitted values or predicted values from the model. So that's what this equation is here. It's plugging in 10 to our regression equation. So plug in 10, you take its natural logarithm, you multiply by the parameter estimate, and then add on the intercept, and you get 18.4 as a predicted value when x is 10. And then you do the same when x is 20, and you get 32.4. Okay, so quite a big increase in y, in expected y, from 18.4 to 32.4 for a 10 unit increase in x. But if we look at a 10 unit increase in x when we go from 150 to 160, now we get a much smaller expected change in y, from only 73.1 up to 74.4. Okay, so how could we look at that in a picture? Well, what I could do is I could calculate those fitted values and then draw those on a line graph. So that's what this is. So that's a visual impression of these calculations that we're doing here. So when x goes from, say, 10 to 20, y goes from down here all the way up here. Whereas when x goes from 150 to 160, then expected y only goes from here up to here. Okay, so a firm might look at this and go, okay, well, if I'm not spending much money and I increase my spending, I get a lot of bang for my buck. I get retained impressions going up quite steeply. Whereas if I'm already spending a lot of money and I increase, I don't get that many more retained impressions. Okay, so if I'm already spending a lot of money, there's not a lot of benefit to spending a little bit more. If I'm not spending much money, I do get a lot more benefit by just spending a little bit more. Okay, so this is useful information for the firms to know. So this graph here is what I call a predictor effect plot, and we'll come back and talk about those in more detail in chapter 5. So why did this work here? So often, not always, but often, multiple linear regression models work better when predictors have nice symmetric distributions and aren't too highly skewed. And if we look at spending, the spending variable in this example, I'll actually show that in R here. We've got a very skewed distribution. Lots of companies spending small amounts of money down here, and just a few spending large amounts of money up here. And so this type of variable, where we've got something very skewed like this, doesn't tend to work very well in a multiple linear regression model. What is better is if we have a more symmetric distribution. And so one way to transform this variable so that it becomes more symmetric and more amenable to modeling is to apply the natural logarithm transformation, because that tends to spread out low values and pull in the high values so that they're a little closer to all the others. So if I do that and then draw the histogram of the transformed variable, this is what I get. I get something a lot more symmetric, and that tends to work a little better in the model. So in general, it's ideal if we've got some background information suggesting which transformations might be applicable to a particular application. In the absence of that, then we can look at graphs as we just did. We can do some empirical studies and try out various transformations to see if any of them help improve our model. And so some common transformations that you'll see in regression modeling, we've looked at the natural logarithm transformation. Another transformation you'll see, which we'll look at an example next, is polynomial transformations. So this is where we look at increasing powers of x, so x squared, x cubed, x to the 4, and so on. We'll also look at an example with a reciprocal transformation. So this is where you divide 1 by the predictor value. This is where we have inverse relationships. And then another one that you'll see is the square root of x. Pretty much any mathematical function you can think of is possible, and so there are other transformations that are not quite as common as these, but that you will see. So let's look at a polynomial example. So for this, I'm going to switch to R again, and this is the house data, and in this case we're looking at the year that the house was built, and it turns out that in this market older houses and newer houses tend to command a price premium relative to the other houses. And so we know going in that we're probably not going to have a linear relationship between price and age. We're going to have some kind of curved relationship. So how can we capture a trend like this? Well, one way is to, as well as having x in the model, is to add x squared to the model. So note here that in the last example we replaced x by the log of x. In this case we're actually adding x squared to a model but keeping x in the model, and this is known as retaining hierarchy, and there's mathematical reasons why this is often preferred for this type of polynomial model. You keep adding higher powers of x and retaining the lower powers of x in the model as well. So let's do that. So here's model 1 in this case. Okay, so the important numbers that we'll look at, we've got the standard error S, the regression standard error S is 60.01. R squared is not very big, 0.024. Okay, we would hope to do a little better than that. And then we're actually not going to look at the t-statistic for this example. We're gonna do something slightly different. So we'll just focus on these two numbers first. See if we can do better than that. And actually let's look at the data so that we can see what we've just done. So there's the data and there's the regression line we just fit. I don't think that regression line does a good job of modeling the trend in the data here. We actually have to look very closely to detect any kind of trend here. But I would argue there is a bit of a trend, because if we look at the really new houses, so those are the ones down here, they're kind of clustered around between $275,000 and $350,000. These kind of houses in the middle, there's a lot more down here, kind of in the $250,000, down at the $250,000. Okay, and then if we go to the older houses up here, there's not many of those, but these average around $350,000, I would say. Okay, so if we had to draw the trend in this data, I think we would have a curved line going from a little higher on this side, coming down, to track these houses down here, and then going up again to track the older, more expensive houses. So I think that's the kind of trend that we're looking at in this graph. Okay, not this straight line. So model 1 is pretty hopeless here. Okay, so let's go to model 2, where we're going to calculate age squared, add that to the model and summarize it. So now we're getting better predictions. 56.49 is a smaller number than 60.01. We're explaining more of the variability in sale prices. 0.1468 is a larger number than 0.02376. Okay. The other piece of evidence that we have that this model with a curved relationship outperforms model 1 with a straight relationship is this result here. If we look at testing the regression parameter B2, okay, we get a significant p-value less than our usual significance level of 0.05. So in other words, we've got evidence at that significance level that B2 is not 0. So in other words, x squared is useful in this model. There's evidence that it really does have an impact or an effect on y, on the expected value of y. Okay, so I've got a picture here. Let's see if I can reproduce that in R. So I'm going to have to do a little bit of side calculation, and then there's the regression line for model 2. Okay, and it does exactly what we wanted it to do. It's high on this side, comes down, and then goes high on the other side. Again though, model interpretation is a little less straightforward. We could do what we did before and do some calculations, or we could look at a predictor effect plot. And actually the predictor effect plot in this case is, if I just redraw the data, and then I'm just going to add the curved line. This is the predictor effect plot in this case. It shows us how expected sale price changes as age changes. So in general, polynomial transformations, as I say, you just keep adding higher and higher powers of x, but it's rare to go beyond 3. I don't think I've ever seen a model that uses a higher power than 3. And even 3 is pretty rare. Very common is quadratic models just going up to x squared. And then I also mentioned that let's say we had a cubic model with x cubed, you would keep x squared and x in the model regardless of the significance of b1 and b2. Okay, if b3 was significant, you would keep all 3 powers, x squared and x cubed, and this is called retaining hierarchy. And then another common feature of polynomial models is to rescale x before you start calculating the higher and higher powers. And the reason for that is if the units of x get quite large, then if you square them and cube them and so on, you're getting very, very large numbers, and that can create a little bit of numerical instability in the model sometimes. So sometimes you'll find that predictors get rescaled if they're used in a polynomial regression like this. So let's just quickly end up with one final example where we use the reciprocal transformation, and here we're looking at data for cars, and let's just actually look at the data. So we've got engine size, and we've got fuel efficiency in miles per gallon, and we can see that there's a bit of a curved relationship here, and it's an inverse relationship. As engine sizes get bigger, fuel efficiency comes down. But if you talk to an engineer, they're going to say, well, it's an inverse relationship, but it's not a straight line, it's a curved line. And so they would tell you that you've got to take the reciprocal of engine size. Alternatively, you could take the reciprocal of y instead, but for the purposes of this example, I'm going to take the reciprocal of x and put that in the model. So same as before, let's fit both those models and see which one does better. So model 1, untransformed, there's the summary, here's the numbers we're looking at, 1.929 for S, 0.7513 for R squared, and we've got minus 32.47 for the t-statistic. Let's see if we can better those by taking the reciprocal of engine size and fitting model 2. So let's look at the regression standard error, 1.741 now. It's lower than before, so that's good. R squared, 0.7975. It's higher than it was before, so that's good. And the t-statistic, 37.07, it has a larger magnitude than it did before, 32.47, so that's good. So from all three perspectives, we could say model 2 is better than model 1. And again, model interpretation much less straightforward. We could do some calculations to evaluate it numerically, or we can draw a predictor effect plot, and in this case, it's going to look like this. Actually, no, this is the plot showing the relationship between y and 1 over x. But for the predictor effect plot, I actually want to have x on the horizontal axis. So this is what I want. So here's a predictor effect plot for this example. As engine size increases, the fuel efficiency comes down pretty steeply for small changes in engine size. For changes in engine size, say going from 1 to 2, 0.5 to 1.5 to 2, 2 to 2.5, 2.5 to 3, and so on. Pretty steep decrease, but for big engines, as they increase in size, you get a drop in fuel efficiency, but it's not nearly as dramatic as a drop as it was for the smaller cars. Okay, so that's some examples of transformations for the predictors in a multiple linear regression model. We've done some very simple examples with just one predictor, but transformations like this can be applied in more complicated models with multiple predictors. In the next video, we'll talk about, instead of transforming the predictor, we'll look at transforming the response. And then we'll also look at an example where we transform the predictor and the response.